Hello YouTube and welcome to my channel. I'd like to introduce you to the new syllabus that the Physics CAIE exams has introduced from 2022. Well, firstly I'd like to just give you a little background about who I am. I've been teaching physics for the last 15 years and currently the lead teacher at Dulwich International School in Zhuhai. I'm also an assistant examiner for Cambridge exams and a graduate from the prestigious Harvard Graduate School of Education. So today we're going to try and do a couple of things, and some learning outcomes that we expect from today are to talk about the universe and to talk about stars and look at some important definitions and the pinhole camera. We want to talk about Wien's displacement law and the Stefan-Boltzmann law, and of course the Big Bang. So welcome. The first thing that I'd like us to remember is that learning is a consequence of thinking, and this was said by David Perkins. He's one of my favorite educationists, if you want to call him that. So education is ultimately what happens between a teacher and a learner. It's got to be a mutual relationship whereby traffic flows both ways, and we listen to each other and we learn from each other. So that's going to be the basis of my lesson today. Learning is a consequence of thinking. So I hope that we can all stay tuned and watch it all the way to the end. The CAIE also talks very, very clearly about the key pillars of the syllabus. And I'm just going to give you a minute to look through what these 5 key pillars are. Alright, so welcome back. There are certain very important parts of knowledge that we need to have when we talk about astronomy and cosmology. And the first one obviously is we need to be aware of the electromagnetic spectrum and basically know about what electromagnetic waves are. We also learn about spectral lines in A2 physics with quantum mechanics. We need to know about the intensity of a wave with respect to how it relates to amplitude. And this was done last year with AS physics. And of course the Doppler effect, whereby wavelengths change and frequencies change depending on who's moving, whether it's the observer or it's the source of sound. So with this prerequisite knowledge, I think we're able to understand what we're just about to talk about. So what is the size and mass of the universe? As a matter of fact, what is the universe? Well, the universe is all there is. It is all that exists. And you can imagine how much that would be. In terms of what we know and what we have measured, scientists say that the universe has about 10 to the power of 11 galaxies. That's a lot. And each of these galaxies could have about the same number of stars, 10 to the power of 11 stars. And on average, one star is about 10 to the power of 30 kilograms. So what is the approximate mass of the universe? Well, that's a question that is very common and very commonly spoken about. I think you can figure this out, and you can see that we will need to multiply the mass of one star by the number of stars by the number of galaxies. And that's a huge amount of mass. Andromeda, apparently, is the closest galaxy, and this is going to take 2.3 million years for light to move from Andromeda to the Earth. Please remember that light is moving at 300 million meters per second. And with that speed and with that amount of time, and remember the 2.3 million has to be converted into seconds, it tells you how far Andromeda is, and it is amazingly far. Alright guys, so we are part of the Milky Way galaxy, and we all know that. I'm just going to give you a few more facts. The Fault in Our Stars, that's a movie I like. Well, these are the facts about stars, and these are 5 important things that I want you to remember. I'm going to give you a minute just to look through these facts, but maybe very quickly as you look through them, say a thing or two. Remember, stars are different sizes and brightness. And remember, stars are not the same place. They're not the same distance from one central position. When we measure the distance of stars from the Earth, it keeps changing. So we know that stars are located at different places from the Earth. Of course, stars don't all have the same power. Later in this lesson, I'm going to show you how the luminosity or the power from a star depends on its size and on other factors. Okay? The Sun, obviously, is in our solar system, and so it is the nearest star to the Earth. These are important facts to remember. It's very basic, but very important. Well, let's go on to the definitions. As an assistant examiner with the CAIE, I can predict that these will be, or this will form part of what you might be asked to define. And so the first one, what is luminosity? Luminosity simply means how much power a star gives per unit time. Hence its unit is joules per second. What is a standard candle? Well, a standard candle is a large astronomical object that has a known luminosity. And there are 2 types of standard candles. The first one is a Cepheid variable star, and the second one is a type 1a supernova. So these are types of stars, and we need to understand the difference in meaning for these stars. A Cepheid variable star is a star that has a periodic brightness and a periodic less brightness. So you have a very bright star, and then it appears dim at one point, and then it gets bright again, and then it becomes dim again. Well, what's happening to this star? It is likely that the helium that is inside this Cepheid variable star is heating up and cooling down, and as it does this, it is expanding and giving a lot of bright light, and then it sort of contracts and gives a less bright light, and this gives that pulsating nature of the Cepheid variable star. The type 1a supernova is a star that is going to explode towards the end of its life. Remember, the type 1a supernova is a white dwarf, so when it explodes, it's going to scatter a lot of its matter and energy out into space. The luminosity of this star, however, stays the same. It does not change the way the Cepheid variable does. And therefore, because we know its luminosity, it is possible for us to make measurements and find its distance or estimate its distance from the Earth. So please remember, there are 2 types of these stars, which we call one as the Cepheid variable, and the second one is the type 1a supernova. Another important definition is that we need to know what a light year is. I think everybody knows what a light year is. I'm just going to say this, that the light year is the distance traveled by light in a vacuum in 1 year. Obviously, the speed of light is 300 million meters per second. If you know how many seconds there are in 1 year, then you can be able to use the equation, distance is speed times time, to find the length in meters for 1 light year. Let's keep going. Number 6, the radiant flux intensity. This is basically the radiant power of the light from a star that is falling or passing through a certain amount of area. Now, what you notice about this is that the radiant flux intensity, which is denoted by the letter F, has an inverse proportionality to the distance from the star, and it follows what we call the inverse square law, whereby when you double the distance, the amount of radiant flux intensity is going to reduce by a factor of 4, and this is what we call the inverse square law. I've spoken about the inverse square law because it tells us that F and D are inversely related, and remember, every time you double your distance from the star, the F, which is the flux intensity, will reduce by a factor of 4. We're going to talk about the Stefan-Boltzmann law later, and you will see clearly how this relationship works. Well, the next one is a black body. A black body is actually an ideal object. It is impossible to have something in your hand right now, or wherever you are, and say, look, this is a black body. No, when we talk about a black body, we're actually talking about an ideal object. And this ideal object is the type of object whereby when you have all the electromagnetic radiation falling on it, it will absorb all this radiation. All right? It also has an emission spectrum, and remember, emission spectrum is something we learn in quantum mechanics. It also has an emission spectrum and intensity that depends only on the thermodynamic temperature. When we talk about the thermodynamic temperature, we are referring to the temperature on the Kelvin scale, which does not really depend on the property of the material. Okay? If you've done your topic on ideal gases, then you know what thermodynamic temperature is. So remember the following assumptions about stars. The first one is that the luminosity of the star will depend on its surface temperature and its physical size. Also remember that the power of the star is uniformly radiated through space. And also remember that as the power of the star starts from its surface and moves towards the Earth, we assume that not a single bit of power is lost. So it is really negligibly absorbed. None of it is lost. It comes all the way to the Earth. These are assumptions. It is possible for us to also think about the size of our stars. So how do scientists measure and say to us that the sun has a mass of approximately 10 to the power of 30? And how are we able to tell that you can put in so many Earths inside the sun? Well, all this happens from observations. And the way we observe is by using simple instruments. In this case, we're going to use a pinhole camera. This is going to help us to make an estimate. Remember, this is an estimate of the size of the sun's diameter. So this is an example of a pinhole camera. There are very, very important attributes to the pinhole camera. Usually the object is going to be much, much larger than the image. The image is also formed and it's inverted when it's formed on the screen. So if we were to take this example or this situation and use this situation in a real life situation like finding the diameter of the sun, then it is possible for us to observe the sun, which is very far away from us, using a pinhole camera, allow the image of that object, which is the sun, to form on a screen, and then we can use simple trigonometric relationships to find the diameter of the sun. In our case here, we will form an angle which looks like a right angle, although we know that the light is coming in as an isosceles triangle, and using the tan of the angle beta in this case. And remember, beta is the angle between the rays of the light as they meet in the pinhole camera, we're able to use the tan of beta as d over x, and this gives us the ultimate estimate of the diameter of the Sun. Right. We have two very important laws when we think about astronomy and cosmology. The first one is Wind's displacement law. What does this tell us? It tells us that the black body radiation curve for different temperatures peaks at different wavelengths, and it shows the difference between the different wavelengths for black body radiation and how they relate to the thermodynamic temperature. So in short, when we talk about Wind's displacement law, we say that you simply need to multiply the wavelength from the black body radiation to the thermodynamic temperature. All right? And this product of wavelength of the black body radiation and the thermodynamic temperature will give you a constant. You need to remember this constant, ladies and gentlemen. The constant is 2.9 times 10 to the negative 3. And Wind's displacement law helps us to relate the color of the star, the observed color of the star, and how it relates to its temperature. I'm going to share a table with you here, and you can see that when a star has a blue color, that means that it has a surface temperature that is very large. In this table, it says much greater than 33,000 Kelvin. So a blue color shows a very hot surface temperature. A red color, on the other hand, shows a rather cool surface temperature for the star. So the range is from red to blue, with other colors like orange and yellow and white. Please remember that when you see blue, that's a very hot star, and when you see red, that is a relatively cool star. So this is the Stefan-Boltzmann law, and this Stefan-Boltzmann law tells us how we relate the luminosity of the star to its temperature. And what you can see here, what you need to pick from here, is that the temperature is raised to the power of 4. The other values are constants, so 4 pi is a constant, and mu, that Greek letter there, is the Stefan-Boltzmann constant, and r is obviously the radius of the star. Please remember this. This is going to be very important to do certain calculations. So let's talk about the Big Bang. A lot of us scientists believe that the Big Bang was the origin of the universe. And what is the universe? The universe is everything that there is. So there was a point in the life of the universe where there was a huge ball of gases, and this huge ball of gases was under a lot of pressure, and after that, the pressure was too much, and the big ball of gases exploded, and it was extremely hot, and that was the beginning of the universe. It is much like thinking about throwing a stone inside a pond, and at the point where the stone hits the water, that's the beginning of the wave, and the wave spreads out, and the ripple of this wave carries on and on and on and on over time. So when we observe the universe, we're able to see and have evidence that the Big Bang actually took place. I want to share some of this evidence with you. Remember that we have some fundamental particles such as quarks and fundamental forces such as gravity, which came into existence right at the time when the Big Bang theory took place. Alright, so we have the Big Bang. There's this huge ball of gases that has exploded. It has spread all its energy all across the vast dimensions of space. And as scientists today, we take a bit of time and we observe what is happening to the things around us. And one of the things that we're observing is the galaxies that are around us. And we can see that the galaxies that are far away from us seem to be moving farther and farther and farther away from us. That is enough evidence that the universe is expanding. And when we talk about this expansion, we can be able to measure the light that is coming from these galaxies that are moving far away in the universe, and we can see that the wavelength of these, the light that is coming from these galaxies are towards what we call the red shift, because they are a little longer than what we observe in the laboratory. So this is the red shift. The red shift offers very, very strong evidence that the universe is expanding. The expansion of the universe offers further evidence that the Big Bang actually took place and it started from a central position. Well, how do we relate the red shift, which is evidence of the expansion of the universe, and Hubble's law? Remember, we have many large and very elaborate stations in space which are observing the universe and giving us evidence back on Earth on how the universe is expanding. Well, as I said, the red shift is the increase in the observed wavelength of the electromagnetic waves due to what we're calling recession. Recession means that the observed galaxy is receding, it is moving away from us. So if that's the red shift, then it is possible to say that the speed of movement of these galaxies is comparable to the distance from us in such a way that the bigger the speed, the farther these galaxies are away from us. In other words, v, which is the recession speed, is related to the distance away from us as observers from the Earth directly. So v is directly proportional to d, and the connecting proportional constant between v and d is what we call the Hubble constant. And the Hubble constant has a value of 2.4 times 10 to the negative 18 per second. It's very important for us to remember this constant. My suspicion is that as a new topic, you will be asked to calculate the Hubble constant or to use the Hubble constant. So please remember that v is directly proportional to d, the recession speed is directly proportional to the distance from the observer, and the Hubble constant is the thing that connects v and d. Very importantly, you need to know that the relationship between the changing or observed wavelength is equal to the changing or observed frequency, which then gives us a relationship of v divided by c. V is the speed of the galaxy and c is the speed of light. Of course, lambda is the emission spectral line and d lambda, delta lambda, is the change in wavelength. Further evidence of the Big Bang. My suspicion again is that these 3 points will form a key part of the questioning for the upcoming June exam. Please remember that we have observed that distant galaxies appear to be moving much faster. Secondly, when we look into space, we can observe that there are many receding galaxies, which gives us evidence that the Big Bang took place and other galaxies are moving away from us. And on average, the temperature of the universe is about 2.7 Kelvin. So that shows us that the universe is very cool. 2.7 Kelvin is way, way below 0 degrees. So we have a very warm Earth, and we also have a universe that is pretty cool. There's a lot of cosmic microwave background radiation that is showing that there's a lot of cosmic waves that were left when the Big Bang took place. And this is obviously due to the heat that was there at the start of the Big Bang. We are almost coming to the end of this. So it is possible for us to calculate the mass of the universe. You remember I spoke about this at the start. When you do the calculation for the mass of the universe, there's an order that we're going to be talking about. It is almost twice the mass of one little sun. Remember, there's a lot of space within the universe. So if we were to culminate and put everything together, the mass of the universe would be extremely large. Also, the distance from the Earth to the edge of the observable universe, and I'm talking about the observable universe, would be almost 4.6 billion light years. I'm sure you can easily change this into kilometers. Well, thank you very much for listening. This is going to be a part of my first video that I'm going to be sharing with you and getting you ready for the exams. So please check out my other videos which are going to be coming out to you very soon, and please subscribe if you like this video, and let's carry on and do our best for the CAIE exams coming out in June 2022. Thank you very much, and bye-bye. Thank you.